I'm going to be talking about the work we did about studying the location privacy threats that the apps that you run pose. I've done this work with Huan Feng while advised by Professor Shin in the University of Michigan. So, all of us run mobile apps. Mobile apps access our location. These mobile apps accessing our location can pose lots of privacy threats, from tracking you, profiling you, getting your home and work locations, and a huge privacy array of threats that we've read about. And it's now mainstream media news as well. We read about it all the time. And it's a huge concern for lots of users, as surveys show, and on and on and on. So, given this current state of threats, what can we do about these threats? As a community, we've been busy doing location privacy threats research for the past 10 years or so. We've also developed lots of cool privacy protection mechanisms that achieve some privacy guarantees, like Mockdroid, Cache, Koi, and our own LP Guardian. Unfortunately, not lots of people use them. The main reasons are that most of these mechanisms have not been implemented with real-world apps in mind. They have not been even tested with real-world apps, and most of them are very difficult to deploy. They require custom ROMs, routing your device, and etc. Given this current state, we're basically left with what operating systems provide us in terms of location access control mechanisms. As you already know, Android used to provide, or still provides, an install time permissions, which they're going to be changing in Android M. As you know as well, you install an app, you have to agree to a set of permissions, and once you agree to these, you cannot change them or revoke them. Starting from Android M, Android is providing a per-app location switch. You run the app, first time you use it accesses your location, it's going to ask you to allow or prevent, and then you can revoke this decision at any point of time. iOS is having this permission model since day one. Recently, iOS has also introduced another location access control, which allows you to control whether an app can access location while running in the background or not. So related to that, there are two questions that we intend to answer throughout this talk. Are these OS controls effective in protecting your location privacy? And if not, how can we improve them in user level without modifying any app or the underlying operating system? So to get there, we need to measure the current state of location privacy threats, which means we need to analyze how much location does these apps access about you, and what are their location access and usage patterns. Then we're going to quantify these threats using different metrics, and use these metrics to identify how much these OS controls are effective. And then we're going to propose LP doctors that tries to fill the gaps in these OS controls in a usable manner. LP doctor leverages this control to balance utility, usability, and privacy. It's worth noting that our measurement and LP doctor are Android specific, but the conclusions and insights that we're going to present apply to different mobile platforms as well. So we're going to start with the measurement thing. So what's different from analyzing mobile traces is that apps are don't exactly sample your location every second or so, or don't uniformly sample your location. You run different mobile apps differently. So to understand the location privacy threats posed by mobile apps, you need to see how much location every app is collecting. In a perfect world, you can instrument Android, run a collection study, collect some data, and analyze it, which means that we have to distribute phones. This doesn't scale that well. We need a scalable way to collect lots of data about how much apps are accessing location. So to get around that, we started with a simple observation. In Android, or any mobile system as well, each app runs in different states. It can run as in foreground, cached by the operating system, or can run in the background as a service. Now, these usage patterns are a function of the user, how the users run different apps, and this can be collected using user-level methodology. Now, while running in every state, each app can access location using a different granularity and frequency. These functionalities are basically what we refer to as location access patterns. These are function of the app and can be analyzed offline. So what we did is we collected user-level data about how much they are using their apps. We analyzed the apps they use in an offline matter to study their location access patterns. And overlaying these on top of each other, we got our app tag location traces, which look something like that. So at each instance of time, this app accesses your location with the following granularity. We analyzed the location access patterns of 1,160 apps, basically the top location-aware apps on the Google Play. We also analyzed each app, how it runs, when it runs, how it accesses the location, and we also analyzed the granularity by which granularity it needs to provide the location-based functionality. So the first thing we observed is that, which is already a known fact by now, that mobile apps abuse the location permissions. Out of 48% of the apps that request your find location permissions, course granularity is more than enough to provide the location-based functionality. A clear example are weather apps. We also observed that a minority of the apps continuously access your location, which is good, means that they behave well. And most of the apps access your location when you run them in the foreground. That is, when you run an app, it either spontaneously accesses your location or in response to some UI event. And for that purpose, we're going to be focusing on foreground location access throughout this talk. The second part of our study is to collect app usage patterns. And for that, we need some data sets. And we need basically a list of app sessions. A user ran this app at that time for that long, and the place IDs that he used the app from. We relied on 3 data sets for this purpose. Our own data set from University of Michigan, we had 25 participants over the period of 1 week to 10 months. Then we recruited 95 users from Feng Lab, which is a test bed provided by researchers in sunny Buffalo. And we also, for reference, we also relied on the live lab data set from Rice University. It's worth noting that we didn't collect the absolute location traces of people. We clustered the location on the device and collected place IDs to further protect the privacy of the participants. Studying these app usage patterns and the location access pattern, we got the following major observation. App sessions tend to be short. So we observed that most of them are less than 5 minutes or less. And more importantly, we observed that 98% of these app sessions started and ended at the same place, which is to say that the user doesn't change his place while using an app for 98% of the time. So as such, we were able to model an app session as being equivalent or corresponding to a place that you visited, which is very important as it allows us to model your app usage or the location access patterns of an app as a histogram, which is basically as shown in the following map. This is how an app looks at your mobility. You visited that location for this many times, this location for this many times. And since apps don't continuously access your location, they have very limited tracking capabilities, as we're going to see later. But this histogram has some significance, as we're going to see in a couple of slides. And it's worth noting that this histogram is basically a sample of your user mobility, albeit not a uniform downsampling of your actual user mobility. So having presented a model of how different apps access your location, we need to quantify how much of a threat is every histogram poses. Now the problem with that is we don't actually know how mobile apps are accessing are processing your location on the server or on the cloud side. We know they access this much location, but we really don't know what's happening with that location. But what we know is how much this histogram or this mobility view is close to your actual mobility pattern. Because the closer it is, this means that the app can describe you better. And for that reason, we focus on 4 metrics that capture and quantify the users and quantify how much the app's histogram matches with your mobility pattern, which is also evident in this map. So that's my actual mobility pattern in Ann Arbor. As you can see, these blue circles signify places that I visit with different probabilities, the darker, higher probability. And this is like a histogram of an app, how much it observed me visiting every location. The closer the bars are to the circles, the more the app can describe me, the better the app can describe me. And we quantify this using 4 metrics. The first one is a very simple metric, the portion of the places that the app can observe I visit. I visit 10 places throughout like 10 months. The app observed me in 3 places, so that's the ratio 3/10. Another metric is looking at a particular subset of these places that we visit. Psychologists, social scientists have observed that places or that abnormal behavior tend to be sensitive because they kind of hint at a deviant behavior, and and applying this to our context, places that you visit with a very low probability are abnormalities from your location, from your regular mobility pattern, and we see how much each app can identify from these places that you have low probability of visiting. Since we're talking about how close each histogram are to our mobility pattern, it makes sense to actually quantify the distance, which we use through the KL divergence metric. And that, as I said, quantifies the distance between the histogram and the mobility pattern. In some circumstance, we need to see if this histogram actually poses a threat, yes or no. We don't want to put a threshold on the KL divergence. So what we did is we just relied on chi-square goodness of fit test. If the histogram is a good fit to the original distribution of the places that you visit, means it poses a threat, otherwise it doesn't pose a threat. And we use the chi-square test with the universal value, the value that everyone uses, of 0.05. I'm not gonna go deep into the measurements and into the graphs. These are in the paper, but I'm just gonna talk about the different insights we got from every metric. So from the first metric, on average, for every user, 20% of your apps can identify most of the places that you visit. And as well, most of the apps were able to identify the top 2 places that you visit, which tends to be typically home and work. Previous research have showed that these top 2 POIs, or these 2 top places that you visit, are enough to identify you. From the sensitive POI metric, we also got that around 20% of the apps identified most of the sensitive POIs that you visit. And we also analyze app analytics, advertisement analytics libraries, which tend to be, in which we have a certain library embedded in different apps, being able to aggregate your location data from different apps. It makes sense that these libraries were able to identify more of your sensitive points of interest. As for the third metric, which is basically the KL divergence metric, we got several interesting facts. The first basic one, which I put second for some reason, that the third-party libraries tend to pose higher threats, which makes sense. They aggregate data from different sources. We also found some interesting fact that there is no correlation between app usage frequency and privacy threats. So running the app more frequently doesn't mean that you're gonna face higher location privacy threats, and vice versa. If you don't use the app that frequent, doesn't mean that you have less privacy threats. And that's because it's a function of many things. It's a function of somehow how frequently you use the app, where do you use the app from, how diverse is your mobility pattern, what the granularity the app is accessing the location at, and other factors. And what we also found is that although for most of the apps, the values of this KL metric is somehow around 1 bit, but the values are mostly larger than 0, and for 20 to 30% of the apps, the value are significantly larger than 0. That's very important, because if histograms were just downsampling of your location trace, then the distance should have been 0. The fact that the distance is not 0 means that the histograms are not just uniform downsampling of the location trace, which is to say that this methodology of studying app's location access or the app's view of your mobility trace is different from what people have done, mostly have done just from studying location traces. So having quantified these threats, we're ready to answer our first question. Are these OS-based controls effective in protecting your location privacy or not? We started by studying the Android location permissions, and to no surprise for everyone, they do actually fail as a notification and choice mechanism. We're not looking at them as a notification and choice mechanism whether to install an app or not. We're looking at, okay, the user installed an app, and the user knows or supposedly knows that this app accesses find location permission or course location permission. Does that impact his usage pattern? Does that impact how much he's using the app or where he's using the app from? We found that for apps with no location permission, for apps with find location permission, for apps with coarse location permissions, these usage patterns, the metrics are basically the same, meaning that the user is not altering his usage pattern based on any location permission. And this should not come to a surprise to anyone, and to Google as well, as they have already changed the permission model to an iOS-like one. More interestingly, the background location blocking of iOS is pretty effective, because just studying the location access patterns or the privacy threats from foreground location access, we were able to find that this limits tracking to less than 10 minutes a day. So if you block location access in the background, apps won't be able to track you for more than 10 minutes a day, which is pretty effective, but won't be able to thwart what we refer to as the profiling threat, or this histogram matching thing. Also, we studied the per app permissions. We studied how much you need to block location for each app to thwart the location privacy threats posed by advertisement analytics libraries. We found out that on average, to block one library or to be able to prevent the location privacy threats of one library, you need to block location access to 10% of your apps, basically which accounts to 50 to 70% of the apps packing this library. And besides, which is a fact that has been also discussed yesterday, these per app permissions are take it or leave it situation. They don't allow users flexibility in terms of utility and privacy trade-off. You either allow an app to access your location or not. And users tend to like more flexibility. They would like to enable or disallow location access depending on the context and in different situations. And so basically the current situation is users can't really control when or where an app can access their location. And for that purpose, we propose LP Doctor, which is a completely user-level tool that the user can download from Google Play to mitigate these threats. So as we found out, that per session location access control is needed. It provides users with better flexibility. It gives them better trade-off between privacy and usability and utility. But existing operating systems don't provide an easy interface. And even if they do provide some easy interface so that whenever you run an app, you can allow or prevent location access, estimating the threat is another different story. The user can't actually estimate whether it's safe for him to enable location or prevent location. Besides, the controls are like 0 or 1, enable or disable location. And our solution is LP Doctor, which is a tool that leverages and complements the existing OS controls, like the background location access, and it's also very easy to install. It's just like downloading an app, and it is easy to use. Before we get into the specific of LP Doctor, there are some limitations because it's a completely user-level tool. So we consider honest but curious adversaries, which have been also referred to as authentic apps in literature. These are apps that have no intention of engaging in a malicious behavior, but they are just going to access your location and try to learn more about you. And we also assume that they access location only through the location APIs. They don't use the device power analysis to access your location. But we can do something about apps accessing your location through Wi-Fi. And as I said, we focus on foreground location access. Since it's not really effective to do background location access, but different platforms, as I said, iOS is actually providing background location access control, which kind of complements our mechanism. And we choose, for obvious reasons, to trust the operating systems and cellular operators, because there's nothing that can be done without such trust. Basically, LP Doctor is very lightweight. It will only interact with you and do processing in 2 occasions. The first occasion is when you install a location-aware app, and the second occasion is when you run such an app. In the first occasion, it will just ask you for your privacy preferences, which includes allow, prevent, or protect location when dangerous. And the user can provide a protection level which assesses his own valuation of the trade-off between privacy and utility. The second occasion is that when the user runs an app. So when the user runs an app, LP Doctor needs to invoke or needs to enforce privacy protection before the app runs. Because if the app runs and the app accesses your real location, then we just lost the game. And the way we achieve it is through instrumenting cyanogen mode or custom app launchers. Because iOS and Android provide you with custom app launchers, and these custom app launchers actually run the app. So we instrumented the cyanogen mode app launcher so that whenever a user attempts to run the app, we pause the execution and divert it to LP Doctor, which takes over, decides which is the user preference from the installation menu, and goes ahead to analyze the threat if the app were to access location from the current location. It's pretty much not that difficult. It gets the profiling continuous metric, which is based on the KL divergence test, from the original histogram, which LP Doctor is monitoring, and the histogram if the app were to access location. If this distance is larger, if this distance is getting larger, means that the app is not going to pose higher threats, in which case we release the location. Otherwise, we need to do something more. Now, the distance is smaller, but that doesn't mean the threat is definitely there. And for that purpose, we rely on the chi-square test, which tells us if there's a definite threat or not. If there's no threat, then we do nothing. We just release location. If there is a threat, then we do have to protect users' location. The way you protect users' location is relying on the indistinguishability mechanism that was proposed 2 years back in CCS. Basically, it's shown that if you add 2D Laplacian noise on a location sample with a certain noise level, it is guaranteed to achieve location indistinguishability within a certain range. And to enforce this location, this newly computed location to the app, we engage Android's mock location provider, which is achievable and just needs a developer setting enabled. But there's a caveat for people who are more aware of this work. You can't really do the Laplacian thing every time because it leaks more information. So once we do it once for a certain app with a certain location and a certain noise level, then we remember this and then we invoke the same one whenever needed. Whenever this protection is engaged, it displays a non-intrusive notification to the user, informing him that a location is being added. The user can choose to remove the noise. And one of the novelties of our design, the user can actually reduce the noise level to control the privacy and utility trade-off. And we do remember these decisions for future usages. This works like a volume knob. If the volume is too high, you just reduce it. If the noise is too high for your app, you just reduce it so that there is noise, but it is enough to achieve a location-based functionality. Whenever this is done, the app launches. The whole process takes 25 milliseconds, on which we evaluate on S4, Galaxy S4 and S5. End of the app session, we update the app histogram, and we disengage the mock location provider. So to actually test this, our main focus here on providing something that's usable. We did a user study by which we recruited 227 participants from Amazon Mechanical Turk. They used LP Doctor with Yelp, 120 users with Yelp, 122 with Facebook. Obviously, some users engaged in both tasks. On average, every user took like 20 minutes to complete the task and was compensated for $3. The user study procedure was as following. The user was asked to install LP Doctor from Google Play, enable mock locations on Android, which is a one-time effort, then reinstall Facebook or Yelp to engage with the installation menu, and then engage in one of two tasks: search for a restaurant using Yelp, or check in from a nearby place using Facebook. And this allows us to study the impact of the notifications and quality of service. So for the installation menu, over 75% of the users found it's usable, informative, provides them with more control, it's useful, and they would like to use it again whenever they're installing an app. And it's worth noting that this appears only once for 5 installed apps. Similar results for the notification. It's usable. Facebook and Yelp users found it that improved their search results, and they would like to use it again. And this appears only for 12% on average for the sessions, which means for these 12%, it needs to anonymize location. We asked users to evaluate the quality of service. For both Facebook and Yelp, users found that it runs normally. The results were relevant. They noticed no change in their user experience, and the course location is enough to provide the location-based functionality. Finally, we asked them some questions after they finished the study. Yelp users overwhelmingly said that they were more comfortable with the app accessing their course location. So did the Facebook users. And finally, we asked them if they would like install an LP Doctor or similar tool now. And overwhelming 78% of the users said now they have no problem in installing an app, such an app or a similar tool. And in conclusion, location privacy is a problem. People are more aware of it. There's nothing they can do so far about it. They just can't do what OS controlled them. We found that they are not that effective. There are many gaps in them. We proposed LP Doctor, which tries to complement and fill these gaps, and which we tested through a user study, which users found to be effective, and they would like to install it. For future work, we would like to do more thorough testing on LP Doctor in the wild to study what are the deployment challenges related to deploying a location privacy enhancing mechanism. And by that, I'm ready for your questions. Thank you. Okay, and the app is open source on GitHub. So if anyone is looking to work on it, I'm also ready for that.
Hi, Grady Clark. I have a question about the very first chart you showed. You had a probability of you visiting a location and an histogram. Your second location of highest probability had no location disclosures. So I'm wondering why that was.
Yeah, so it's basically a location where you don't use the app from. That's it.
Hi, I'm Nectarius from Facebook. I'm wondering what's the statistical significance of your user study.
Of what?
Of the user study. I mean, those percentages of how much more happy the users were with the new.
So basically, what we did is we asked the participants a question, like how comfortable are you with with Facebook not accessing your very fine location. I'm just reporting the percentage of the users saying they are comfortable. Basically, it was a scale from 1 to 5, and we counted the users comfortable as those saying 1 or 2 on the scale.
Okay, but can you extrapolate this to a larger user base? I mean, what's the?
I mean that depends on the sample of the people we got.
Exactly. Yes.
Yeah, and that's which is good because I have a demographics slide. Just a second. Basically, it's not very representative of a general population. As you said, it's very skewed the distributions for gender, age, and education. So I'm not really sure if this extrapolates to a general population.
Okay, thank you.
You're welcome.
Hi, Michelle Mazurek, University of Maryland. I'm curious, you talked about locations that you don't go to as often being more sensitive.
Yeah.
Do you have any evidence for that? I'm not sure I'm completely convinced, because I could imagine, let's say I was having, an illicit relationship with someone that I would see them frequently, right? On the other hand, places I don't go that often maybe are like the airport or, here for this conference or something, which is maybe not very sensitive.
Yeah, the fact that we didn't collect absolute locations, we couldn't confirm that pretty much accurately because we didn't have the absolute location. And looking at this absolute location would be more privacy infringing. What we did is we just started with this premise in psychology that says that these tend to be more private, but we didn't actually confirm that these are actually private. So,
thanks.
You're welcome.
In your user study, did you do anything to try and control for acquiescence bias or the Hawthorne effect? So it was clear that the subjects knew what was being studied, and so just asking them, do you like this tool, you're very likely to acquiesce to that.
Yeah, I mean that was the last question. So what we were actually focusing at is to study when they ran Yelp, did a search, there was noise, how relevant the locations were. So that was like the main question that we wanted to answer. But as for the last question, yes, I do agree we didn't account for biases there.
Okay, thanks.
Hey, Tamara Denning, University of Utah. So it looks like, from what I saw, the questions that you asked were ones in the user study were ones that you created yourself. Is that correct?
Yes.
Okay, is there any particular reason you chose to go with those questions instead of or in addition to some of the more standard usability skills?
That's a good question, but so the thing is, we're not really collaborating with a dedicated HCI group there.
Okay.
So we had to go with the tools that we already know. So
Okay. Thank you.
so yeah, we didn't go with standardized usability test there.